Good morning, everyone, and I appreciate you all getting up early, and welcome to the Wolfram Technology Conference. As I said, this is a new way of presenting, but it might be a modern way, and it obviously has certain advantages, though it's nice to see people and talk in person. Right, let's just get started. This talk is about the Wolfram Compiler, and I want to talk about things such as its operation and its benefits, some of the strategic goals, and some of the latest advances. Now, there's a bunch of related talks to the compiler. So this talk that I'm giving now, a bit later this morning, actually, I think, sorry, I got that wrong. That's good to have a live talk. I can fix it. Mark Sfroniu is giving a talk at 9 CST that's covering optimizing code and some of the arithmetic features that I think will be interesting. And that's going to be followed by a Q&A session that'll be like a sort of live chat room type of thing. And we'll be there answering questions about that. And then tomorrow morning, I'm going to give another talk that tries to focus on some of the high performance computing features in the compiler. So, right, so what is the compiler? It's a compiler for the Wolfram language, and it's a long-term project. I've been giving presentations about this for quite a few conferences. Some of you might remember. It's something that's entirely built in the Wolfram language. So it's now one of the largest complete applications in Wolfram language. It's based upon the very latest knowledge and technology about compilers. So the first version was released in Mathematica 12. There was an update in 12.1, and we're just coming up to a new update with 12.2. So the idea of the compiler is it converts Wolfram language code into native machine code. So that code that runs very close to the metal, the hardware of your machine. It uses a thing called LLVM as the back end. I'm not going to talk a whole lot about LLVM. It's a bit technical. It has a couple of modes of operating. It has like an in-memory JIT version. So that's very convenient for sort of interactive use that fits with the Wolfram language, the Mathematica, eval print loop. But it can also make dynamic libraries. That's useful as well. It's based upon static type annotations, but a minimal set of static type annotations combined with an inferencing technology. And you can think of it as an alternative execution model for the Wolfram language. It integrates very well with the Wolfram language interpreter, but it can also make standalone applications as well. Now, what are some of the benefits of a compiler? So the main one, and this is the thing that everybody's interested in, is you get faster execution. So there's, your code can run a lot faster since it knows about the hardware, and it's able to figure out a whole load of things ahead of time in order to target specific machine technology. You get a guarantee of correctness. This can be frustrating because often it takes a bit of time to get your program to compile and such like. But when it does, you've got quite a good certainty it's going to do what you want. It fits with other code generation systems, and it can leverage. It's a great way of leveraging technology that's hard to access in other ways. And this is one summary that I like to think of it, is it takes a high-level language specification, the Wolfram language, and it combines that with low-level, i.e. fast execution technology. So what is not the compiler? What the compiler is not, and this is source of frustration to people and such like. It's not a magic solution, the way you wave a magic wand and somehow everything gets better, or at least it's not yet reached that. So I just want to try and thread through some of the directions, some of what we're doing and what, the purpose of the individual projects and such like. So one goal we have is obviously to compile Wolfram code. To do that, we have to increase the set of functions that we're supporting. And to do that, we often have to add new types. And I'll be showing some examples of what we do with this. We want to generate fast code. So we have like this base thing based on generating machine code. But we've done a lot of work. So we've been building up this library of things that actually Mark's going to be talking about. We add various special optimizations, and we can access HPC features. That's going to be the focus of my talk tomorrow. We can support new directions in the system, new directions. So we built a DataStructure library. We have tools for automatic differentiation. Some of these HPC things, standalone applications. So these are really quite new directions for the Wolfram language. We can also enhance the existing system. So it's just a new implementation layer for the Wolfram language that might interest people at Wolfram Research or outside of Wolfram Research. So another big goal that we have, and this is something that's negative, not a strong feature at the moment, is the compiler is slow to generate code. It's slow to run. The code it produces is fast, but it's slow to run. Sorry, I'm getting a message from someone. Can someone else fix I'm speaking. Can someone else fix my name in Zoom? Sorry.
Yes.
Right. And so just to rewind to this, the solution that we have, the ultimate solution to improve speed of compilation, is to compile the compiler. Right. Another thing that I think of as quite interesting, I'm quite interested in computer science aspects, especially compilers. I've been implementing Wolfram language and other computer languages for many years, but actually it's a good demonstration. The Wolfram Compiler and the Wolfram system is a good demonstration of why it's a great environment for studying compilers, for doing research and development in compilers, i.e. making new techniques. So those are some of the goals that are going to thread through the talk. So I'm just now going to give you a basic demo. So we take a function and it has these type annotations. So it's just a regular Mathematica Wolfram language function, but I've said that the two arguments are 64-bit integers. And I compile it with a thing called function compile, and I get out the, it executes. Now the original function also compiles, also executes. So this one, but they're taking different paths. The uncompiled one is going through the standard interpreter. This one is using this compiled code function and is using native machine code to execute. Results are kind of the same. Now, in the compiler, these are some things that are a bit different. So we support a lot of types. And for example, we support what you might consider as a byte. So an 8-bit integer. And again, we give markup saying what the input is. It's still the same function plus, but now it's going to select a version of plus that is for, 8-bit integers. We also support half precision floats. So these are real 16. So this is the typical double precision floating point that Mathematica uses, 64 bits. This is a quarter of that. And why do you care about these? Well, actually, there's a lot of application areas in machine learning or image processing where they actually need these sorts of things because they use less memory. So you've got big data sets, you've got images and things like that, and you don't need the full range of the sizes that you have from the full range of sizes. Sorry, the ice cream van has just arrived at the Wolfram the office here. Maybe you can hear it. Right. For each of these types, we can mix things up. So we got different integer types, and I'm doing a bit and things all work. And the benefit of this is that, you know, it's no use having all these different types if they're not fully supported. So that's true. Now, another big area of functionality is array computation. So Wolfram Language has long had a thing called packed arrays. So they look at that, you know, they're sort of, you know, compatible with lists of numbers. And so we have very good support of compiling code with packed arrays. So you say it's a packed array of machine integer, and that's the number of indices. So this is a vector. So now what's kind of new that we have is we also have in the system these things called numeric arrays. And these also hold scalar types. They're somewhat similar to packed arrays, but we have the same support for functional constructs that we have with packed arrays. And actually, I'll just say that the implementation of these is, you know, we can share the implementation. So these arrays, packed arrays and numeric arrays, these are a core way that data is used in the Wolfram language. So supporting those in the compiler is very useful. Here's another key thing of the Wolfram language is that it's a functional language. So we can have, you know, nested functions and do things with them. And this is kind of it's now a pretty standard, many languages have these, you know, support such things. And here I've written, you know, a recursive thing. The only type annotation I gave was on the input, and it can figure everything out inside of this. Again, the uncompiled version. And this is quite nice because I can develop things, code, uncompiled way, and when it's working nice, I can compile it for a speed enhancement. That's quite a good work. And then moving along with the support of functions, you can get all these tangled, you know, so here I've got one function and I'm passing it as an argument to another function and invoking it, and these things work. And same thing, I've got a function here and this returns a function, and these sorts of things all work. Now, these are rather tangled ways of adding, you know, incrementing an argument, but actually they can, you know, they can be quite important. Another key feature of the compiler is to get compilation errors. I'm seeing a few questions. I'm probably going to answer some of the questions towards the end, unless they're totally related to the the thing that I'm showing at the moment. So here, what I have is I've got a program, a function, and I've got a Boolean here. And in one of the branches, so I'm doing a condition, one of the branches, I'm initializing it, and then I'm returning it. And the compiler comes up with an error message. Sorry, I'm just taking getting a bit dry. And there's probably some error in your code. Or here's another one. So I'm invoking the sign function on a Boolean, and it doesn't know what the Boolean is. This is probably very likely an error. And so this is pointing to a new way to find unintended code from static analysis, not from running it. So it doesn't matter if this thing here was reached or not reached. It's you know, it gives an error, and you can go and consider fixing your code. We also have a bunch of runtime errors, and so here's an example of such a thing. So the arithmetic system is validated. So I've got an integer 64 and a signed integer 64. So this is the largest input that I can have. And if we go one higher, we get an error. Now, the default value of version of function compile is that it restarts the computation in the evaluator. So that's why this thing comes back. Now you can actually disable, there's techniques to disable this. So if I do this in an unchecked block, then I get the, the result that you would expect here. But now it stays as a integer 64, but it's wrapped around because it's using, the modular 2's complement arithmetic system. And so that might be an unintended thing, but actually being able to either catch these errors or not care about them is quite important. And actually, when you seamlessly switch under the hood from, sort of machine integers to software integers or to symbolic forms, this is often a key source of slowness when people show me their code and how can they make it faster. Very often they're making big symbolic things in the middle, and being able to detect these is, or even get rid of them, is quite useful. Right, saving to a library. So here I've got a bigger, you don't have to read all of this, but this is an implementation of a quicksort function. So I'm taking a packed array and I'm compiling it into a library, and then I can load the library, and it just loads the library and it returns a compiled code function, and then I apply it to a bunch of things and it's sorting the code. So this sorting actually runs pretty fast. It's not quite as fast as the built-in sort, which actually uses parallel techniques for, divides things up and runs them all in parallel and then recombines them. But for such a simple specification of quicksort, it's pretty fast actually. And the big benefit of saving the library is you don't have to recompile things all the time. You can just load things after the fact. Now, here are some new things that we're going to talk about. So as we want to support more functionality, we're going to need more types. And so this thing here, this is one that not totally optimized for compilation speed. It's a little bit slow. It should come back eventually. And there we go. And quite this slow. There we go, fine. So what I've here is I've got a string and I'm putting it into a list. And I'm doing a string join and the thing. So when we look at this actual compiled code function, what we've got coming back is a thing called a list array. So this is a list array of strings. So we saw packed arrays and numeric arrays. This is something we call a list array. And this is something that can contain anything. So here's another aspect of list array, is that it can work for ragged data. So there we go. And so here I've given a list array that itself contains a list array of integers. Now, if I was using the standard array technologies, packed array, numeric array, then they only contain a fixed set of numerical contents, and they must be rectangular. So this list array can contain anything. It's not only scalar types, and they do not, compound things do not need to be rectangular. So it's closer to the Wolfram notion of a list. So this is pretty useful. Right, now I'm going to talk now about some of the, generating fast code, the fast to execute. I'll probably talk a little bit about this at the end if I've got time. It's a bit hard to gauge the usage of time that that I'm working through. I don't think I'm doing too badly. So one of the ways that we've worked is this is a big thing that's been worked on, particularly by Mark Sfroniu in this version that we're about to release, is a subsystem for arithmetic. And this is, the benefit of this is, so we've implemented arithmetic functions, and these are things that most of you will just imagine you do, you know, x plus y or mod, you know, mod or, you know, sine or something, and you just take it for granted that these things work. But actually, it's tremendous. You know, it's not trivial to make this all work in a consistent fashion. The big advantage of implementing all this in the compiler is that it all gets inlined into one functions, and since the arithmetic is kind of fast to execute anyway, lifting it out from individual function calls is a tremendous, you know, sort of has a lot of speed advantages. Mark's giving a talk about this a bit later today. Right. The compiler is a great technology for adding, you know, fundamentally new technology to the Wolfram language. And some of these, such as the multi-core parallelism, I'll be talking about in the HPC talk that I'm doing later. Now, one new feature that we did add, we started in 12.1 and it's extended in 12.2, is a library of data structures. So these are built, these are coded up in the compiler, and then we pre-compile them into a library so that you don't have to run the compiler in order to create them. And another key thing is some of the data structures are mutable. So just list some of what we've got. We've got some core things like a counter and a value. We have a whole load of container data structures. So this is an extensible array or a linked list or queues and stacks and buffers and things like that. We have a bunch of sets, so bit vector, you know, various hash sets, disjoint sets, sorted multi-set. Now we tend to add them when other parts of the company need, you know, development need a data structure, we can add them. We've got various, this is a binary tree, this is a balanced binary tree using AVL balancing, and this is a general tree, and then we have some key value store data structures. So let's just have a quick, so this is using the Wolfram interpreter, so I can create an instance of, like, this is an AVL tree, and then I can go and insert a bunch of, you know, things into the tree. So one of the nice things about this AVL tree is it balances things. So actually you can see, I mean, it's not optimally balanced because you could probably put this, you know, these things down here, but it never gets worse than this sort of unbalancing. It's kind of the guarantee of the algorithm. And so one of the nice things about these data structures is that you can do computations on them. So sort of, you know, this is one here where I want to, you know, figure out what's the maximum depth. So I can write a little bit of code like that, and then run this maximum depth thing, and I can see the maximum depth is 6. So that means the longest path from the root is 6, which actually looks feasible. So what's new in 12.2 is to add more seamless integration between uncompiled and compiled code. So here, for example, I've got I've written some code that I could write. So this is a function that takes a dynamic array and it's reversing. So there's like a swap part operation of dynamic array, and it's reversed the thing here. And so it's taken these, you know, you can see that it's reversed. So what's quite nice is I can take exactly the same code and I can compile it. And so now it's reversing it. Since this is done mutability in place, then you know, it's just turned it back to where it was in the beginning. So what's quite nice about this is if I make a large, so this is like 10 million data structures, we've got quite a good acceleration. So this is the uncompiled reverse function, and it runs 6 seconds. The compiled version is running nearly 100 times faster. And so this is giving some idea of some of the benefits of the that you can get from compiling things. Quite significant speed ups. But what we kind of like is, you know, it's the same function. You can develop the function, test it out and debug it and, you know, prototype it in uncompiled way and then compile it. And then you could even save it in a library or something. So I'll probably go back to some of the data structures and show some of these when I talk about some of the type system. I think I'm not doing too bad with time. So there's a set of compiler definitions that we write, and then we built a data structure library from them. But there's lots more functions for like sorting or traversing. And if something's not built in, it's easy to add. And then if it's compiled, it's just as fast as if we wrote it. And again, that's one of the things that's always, you know, a goal of the project is that, you know, there's always an impediment for users working in the, you know, they have to wait for us to go and add things internally in the system. With the compiler, that barrier is broken down, and it's quite feasible to write things in the same way that we write them, but they're just as fast. So I think that's you know, advantageous at some cost. So again, another of the goals was to support existing functionality. And by the way, there's a question about how do you know whether the data structure can be changed in place or not. The documentation says whether they're mutable or not. That's part of the, you know, documentation. So supporting areas such as machine learning or numerical computation. We've looked at supporting the cloud notebook system with generating WebAssembly. But there's still a constraint on this, is that the compiler is still very slow to run. So that is a constraint. Now I want to talk about another thing that I think is quite interesting. This might be interesting to people who are familiar with other compilers, but you know, a thing that's an important feature of the Wolfram compiler is that it's integrated into an existing language. And that gives advantages and disadvantages. So one thing it means is that the semantics of the language, the way that plus and times and fold and, you know, module are fixed. You know, we don't have a choice as to how they should work. It also means that since the existing system is, you know, a sort of interpreted system, there's a lot of code that at the outside looks as though it can be ambiguous. And so we've developed ways of dealing with that I think are quite interesting. And then finally, a huge advantage is that the compiler can make use of the Wolfram language environment in which it lives. And there are some lots of neat ways, benefits of that. And that's quite unique in terms of compiled systems. So here's one, I'll just sort of compile these. I've got 2 programs here, and I want to focus on this thing here. So in this one here, f is a function. See, there's f, there's a function there, and I'm giving the function a string as an argument. But in this other one here, f is a data structure, and here I'm calling an operation, like a method call on the data structure. So, but the syntax, we don't have a special syntax for that. We're just using, and this is, you know, like associations have, you know, you can do lookup in an association based upon these sort of sub-value things. So in the interpreter, of course, it's easy because it knows, oh yes, this is this thing, and it can decide what to do. Now, it's actually quite non-trivial, and we had to build in, this is another new thing in the new version, is to develop the technology to be able to disambiguate based upon the context. So when it sees something like this, it has to say, well, it has to spawn off alternatives in the analysis and then bring them to completion. But we did that. And so when we compile this one here, it's able to get one answer, and so it deals with this correctly. And this is something that in languages like the Wolfram language, there are many things like that. And having an underlying compiler that's able to that is super useful. It means that, ultimately, as we build this up, we'll have more ability to compile more of the language. Many other things that we, this is a feature of the type system. Obviously, there are many things as we build up that are going to be challenging, but having this underlying ability to disambiguate what in essence looks like ambiguous syntax is super useful. Now, here's another nice way that we use the Wolfram language. We use the visualization features. This is a bit more something that would be useful for people developing, developing compilers or something. So I've just loaded a little thing for graph tools. So here I've got a function, and what does it do? It's got like a branch, and then there's a loop, and it returns a result. And we can look at, this is the sort of intermediate code that's generated. So this is the, dealing with the exception from overflows. But there's a bunch of branches and things. But it's a bit hard to sort of see all of that. But what's quite nice is to then come and get a control flow graph. So this is just the control flow in one function. So here's the start, and you can see, and this is the end. So every arrow, ultimately ends up here. And actually, looking at this more abstracted view of the code is really useful. I mean, this is something that we really use quite you use an awful lot. But this is making, we've got all this other stuff in the Wolfram language, so we're able to use that in order to develop the compiler and to enhance and gain insight and knowledge. And this makes, our compiler, the Wolfram system, is pretty useful for learning about compilers and developing them. Here's another way, seemingly trivial, but I can use the outer, write programs in, uncompiled scripted programs to build up Wolfram, a set of functions. So here I'm just, iterating over, and I've made a bunch of bunch of functions. And we use this a ton when we're setting the system up. And I know this, so we're using the rapid prototyping system to create things. And doing this in other systems, I know, is astonishingly painful. It's and yet it's so natural in Wolfram language. So that's kind of a nice feature. Here's another feature that we can do is we want to prepare data at compilation time. So here what I'm doing is I want to write a function to test if numbers are prime numbers. And so one way I can do this is I could make a I can make a lookup table. So here I've made a lookup table, and I'm saying, is the thing a prime number or is it not? And then I've compiled this, and so this says, 6 is not prime, but 7 is. So I can do like a test here. So I've been able to prepare data before, and then sort of injected that data inside the body of the function. So that's pretty useful. Now, in essence, actually, just to go a little bit further, there's a lot of redundancy in this. So we can do much better than this. So first of all, this table here, I'm using, you know, like machine integers to hold all this data, but really it's just one bit that's needed. And secondly, so there's a couple of tricks that you can use. So you can avoid the even numbers since there's a very quick test. And then you can pack everything down to one bit. So we can make a table that looks like this. Now this table is completely unintelligible. You know, if I did B 32, you know, 3 or something. So I've just got these bigger tables and things. And then we have to do like reverse. So we did compression of the numbers down into bits. And then when we run the test, so first of all, we check if the input's divisible by 2, in which case we return false. And then the next thing we do is to do the bit shifting, and then we look it up, and if we've found something, then it's, and so we can run this, and you know, 7 is prime. And so what's nice about this is when we compare this with the built-in, sometimes you have to like let these things warm up a bit. It's pretty competitive with the built-in, and this one actually beats the built-in prime, though I would strongly suspect most of the time here is spent in the overhead of accessing the code. So if you were integrating this prime queue into your own code, then it would really start to be very efficient. So just to go back to this, you know, again, doing this, you know, making these tables of data and stuff in other systems is, you know, very painful and prone to error and a source of bugs. You know, I think the famous Intel division error from way back, maybe some of you don't remember this because it was, but that was caused exactly by an error in a lookup table that was used to, you know, for some code. And the closer you can have generation of this data, you could even build some verification, you know, into the compilation or something. That might be useful. The closer your data generation is to its, you know, sort of applicability, then that's going to help avoid errors. Right. So let's come and have a look at the integrating with external code. And so this is something that we do a lot to sort of build out existing functionality. So some of these things, you know, they're not specified in a completely convenient way, but so here I'm calling into the C library on my system, and there's a function there that is gets the time in seconds. So what I've done here is I've added a declaration. I've added a declaration of a new function where it's linked to an external library, and the name in the external library is time. And I've given it a different name here, and here's the type of the function. And so now I can invoke this, you know, and I get a different answer each time. Now this is kind of a trivial sort of thing. Actually, I did just add another example with a, this is another function that takes a, result of seconds, and it returns a string formatting of the result. So this is just, so I'm just calling the functionality that's elsewhere on my system, and it's pretty easy. So just the specification of these things, you know, that's not completely smooth yet, but the concept's very powerful. So we build a lot of extensions to integrate with existing libraries, and then this is how we've been building OMP or integrations into other other libraries that we can do in this way. So it's fairly straightforward. So we just build a big load of these, you know, declarations like this, and then we can start to access them from the compiler. Right. So now I want to talk about the type system. So the idea is we have a type inferencing system. We have sort of minimal markup. We support what we call polymorphic definitions. So a little bit of code can go a long way, and we can create new types. We have a way of creating structures, but not a union type, and that's maybe you're not. And then we also support function overloading, and it has a good way to choose between choices. And I'm going to give some demonstration of this. So now I'm going to declare a function, and this is the name of the function, and it's declared for one type. So there's only a version of this function that takes an integer 64, and that's all it does. Now I'm going to make a polymorphic version of the function. So this thing here takes any input. So it returns the same result. The previous one also returned a string, but this one here takes any input, but it returns a different value. It's still a string, and so there we go. You see, it didn't find that, but now it compiles and runs. So I got that sort of warning saying I hadn't declared it. We can even, in fact, go a bit more, and we can give a constraint on the type. So now I'm saying here's another version of this test function that is defined for if the element is known to be a number. And so now I have 3 different versions of this, and all of the choices as to what things, that's all done at compile time. So it's all very fast. But and even if I went back and recompiled this thing here, it still works. So this selection of different types is it's set up to choose the narrowest type. So that since there's a version for integer, it chooses that. When it's a real 64, it knows that that's an element of that, so it chooses that. And then the Boolean case, there's no constraints, it chose that. And so and this is, again, something that we put a lot of work on into the latest version. But that's a good benefit, and having the thing be sort of deterministic and able to work is pretty useful. So going back to the data structures, another feature of the data structures is that they are, or many of them, it varies, but are especially polymorphic. So here's a data structure, and you can see here, so I've given a dynamic array, and I'm appending a real 64 to the dynamic array, and then I'm returning that. And so the type system, it's figured out that this is a dynamic array that contains real 64s. But if I had a slightly different code, and the thing that was being appended was a string, then now I have a dynamic array of strings. And then if there's no way of figuring this out, so here I've got a function that a dynamic array where there's no way of understanding what determining what the argument is. So it has a default value, which is expression. So that's what we have here. And the benefit about this is that it means that you get fast, efficient code. When you compile code with these data structures, it's quite feasible to be polymorphic, and again, this helps to go from uncompiled to compiled code. Another, this is something that lives in compiled code, is we have a an iterator system. And then we can use the iterators. This is a little bit slow to compile, but we use these iterators to set this up. So here I've got a do loop, and so this is similar. There's other things. If this was a list or something, it would also work. But LM is being bound to each member of the dynamic array. And this is all built on, we have a nice library of iterators, except we call that generically from the, you know, from the implementation of do loop. But again, this is all, if it's known that there's an iterator, then this sort of thing will compile, and that's kind of the same thing. So there's a lot of extra functionality of these data structures, and you know, this is, with this iterator thing, you can write quite general code where it just has to know that it has access to these various iterators. Right. So the compiler is very slow to run. And the solution for that is to compile the compiler, which we're working on very actively. To do this, there's some more compiler functionality that needs to be built out, but a key thing is to tackle more Wolfram language definitions, specifications, and that's the notion of down values. And I'll show that in a minute. But one thing that we have done is to start building libraries of common operations. So this is a trade-off between, it makes compilation faster, but it can hurt execution speed because the code in a library can't be inlined. So this is a trade between compilation time and runtime. But some of these things that don't inline so much, it's not so important. For example, are string operations. And we built a library of string operations. So here I've run a compilation of string join, and this is just calling going to call the version of string join from the library. Now, but if I compared this with another, so I'm creating a type environment and I'm saying don't load any libraries into this. So now there's lots of code. Now this might seem a lot of code, but of course each one of these lines is like one machine instruction on your CPU. So it's, you know, not super fast. And so this is a way that we can speed up compilation by making a trade-off with execution speed. And that's something that I think, you know, can be kind of useful. Right, now let's come and look at some more code. So here's some description about down value compilation. So basically, I want to compile functions that are written with patterns and set delayed. I want to write my code like that and can benefit from the compiler. Maybe there's type annotations, maybe there are not. And we've been working on this. It's not by any means a complete finished system, but there are some benefits. So here I've written the thing, and then I do compile values. And now when we enter something, it goes and looks for a compiled version, and then it generates it if it's not available. If it finds one, then it uses it. So something that's quite nice is that if I have other compiled code, and the other compiled code might itself be embedded in a down value, then it makes use of this system. So it makes, this is accessible. And so now I've got a compiled, I've got a function, and it's calling the f that I just compiled. And so when I generate the machine code for this, it can make use of the function that I already pre-compiled. And then this sort of runs, and that's I mean, this all seems sort of, you know, natural, but this is the way to make these things faster. And here's another a variant where I've actually given a type annotation, so it figures out from the pattern. And I'm going to compile this, and then when I run this, so one of the things that's quite nice about this is this. I mean, I saw this. So I've written the, typical program, and then I did, compile values, and it got a lot faster. And just to compare, here's the uncompiled version. So we're getting quite good, quite good speed ups. So this is, to me, this is kind of the holy grail of, writing code and then just having very minimal access to compile it and getting a benefit. And so this is quite close to the magic that I talked to. This is not a final sort of thing though. So right, but so this is not a ready thing. This is sort of a future thing. But when we can have this natural integration of down values of the compiler, then we can get very significant speed enhancements in the code. Right, I don't have a lot of time left, but I'll just finally look at some ways that we've worked to optimize code, rewriting it and to be faster, or maybe if you're willing to relax some of the input arguments and some of the benefits. So just a quick rundown, the sort of pipeline that we go through. So we start with a Wolfram language program. We convert it into this intermediate representation. We convert it and we give it type analysis. And then we generate this thing called LLVM, and then LLVM generates machine code. So we have various transformations and optimizations in the Wolfram stage, but then there's further transformations and optimizations with LLVM. And one thing we do a lot of work at is to make sure that we're able to leverage the LLVM optimizations as much as we can. So first, here's something that I'm going to do with showing just a code pattern. So these two code functions do the same thing. This one is using a functional construct, and this is doing the same thing, but it's doing a do loop. And I'm going to, so then you have to say, are you paying a price for this? Either in compiled code or, I mean, this is what it does. It just sort of adding up all the elements. So let's compare the speed of execution, and I'm going to give, 100 million input. And so we get the same answer, but the non-functional way, and you can see similar things in Wolfram code. So one thing that we've done, oh, and here's just like a comparison. And actually, I see there's some discussion of the old compiler. This is actually using the old compiler. So for this particular thing, the old compiler is like 10 times slower than the new one, and even worse compared with the the sort of non-functional thing. So we added some special, another optimization level, and this is what comes out of this. So we compile those, and now the functional version has got, hang on, jumping around a bit. This is the functional thing that's written with fold. That's the code you want to write because it's more concise and you don't have to worry about the details of how the thing's done, is actually faster than the, and that's for various reasons. We then inlined various, I won't go into all the details, but we're able to sort of basically turn this into, there's much more inlining. And since there's more knowledge about, it's a higher level description, it actually ends up with faster code. And that's kind of the value proposition of functional programming. So with the right optimization system, the functional is actually winning out, and it's much better to write. So here's another lower level optimization. This is talking about loop optimizations. So again, I've got some code, there's a loop here, and we do repeated timing, and this runs at a certain speed. So we can do some things, we can relax some things. So if I turn off the abort handling, then I make something that, you can't hit Control-C or interrupt the code, but it actually makes the thing run faster. And here's another thing I can do, use an unchecked block. So this is the arithmetic here is running, sort of unchecked. And this is also, so this is faster, both of these are about twice as fast. Now then if you combine these, then I'm going to do the unchecked version and turn off abort handling, then it actually runs astonishingly fast. In fact, it's running independently of the length because this loop here is what's known as an affine loop. And so it can just, replace that loop with the, formula for the result. So this, it's going to be, sort of, the speed is independent of the length of the loop, which is quite nice. And this is just showing that, there are optimizations. This is making use of some of the LLVM optimizations, but there's a variety of technologies and optimizations to work with. There's lots more code optimizations that we could be doing. Right, fine. Just coming up to finish, running out of time. So speed of compilation, current directions needs to be much faster. We need to add union types. I think now we're getting a system that's quite powerful. We do have this manual documentation. One of the nice things that we've added, we have, things like you can look up functions, and so this is like copy to, and it has nice ways to jump off to the input documentation to show you the implementation. Integrating with down values, parallel constructs, they're in development tools, and more optimization. So I'm going to end my talk. So I was showing you some of the goals and benefits and progress of the Wolfram Compiler. I was demonstrating some of the core functionality with types and things in the data structure library, some of the ways that it integrates with the rest of the system, looked at the type system and some of the newer advanced features. And these are some of the other talks. And finally, I'll just have a good thing. We have a lot of opportunities in the company for developers or interns. Working on the compiler, it's detailed for some, but for some people it's completely fascinating. And there's lots of projects, interesting, new technologies, building out the current features and developing new compiler text. So get in contact with the company and come and join in if this is interesting to you. Anyway, I think I'm about to wrap up. I've got a few questions here. Now, this is somewhere I'm just about out. I don't know if everybody has to go off to something. I can also answer some of these questions at a, there's a Q&A session a bit later this morning. So I'll just quickly answer, will the new C system replace library link? I think it's sort of orthogonal to library link, and it needs some build out. So okay, I'll try. Oops, sorry. I'll try to. Thanks, Phil. I'll try to share the notebook. Some of these things are in 12.1. Some of them will be in 12.2, and some of them are going to be sort of future things. the speed of the compiler, the old compiler is useful, but I think the new one now, especially in 12.2, is predominantly faster, but it has tremendously more functionality. Things like that. There's the data structure, and the documentation says whether things are mutable. We've actually started working, this is not ready yet, on some immutable data structures like immutable arrays and immutable sets. And of course, that's what association is. So we'd like to have an implementation of that. But the top level feature association is an immutable hash table. Data structures are useful. There's some questions about GPUs. I think I'll study those. I'm not going to quickly answer that, though there's no GPU, there's no NVIDIA functionality for Apple. That doesn't exist. You should use Linux or Windows machines. Anyway, I think I'll wrap up, and thank you very much, everybody. Great. Okay. Yeah, compile values, Phil, is not in 12.2, I'm afraid. That's obviously an important feature to move in. Anyway, thank you very much. Thank you.